With the theory for these theorems established, now we want to look at a couple of examples where we can see what this looks like for verifying hypotheses for a concrete function interval, and then seeing if we can algebraically determine what the value of c is, or at least one c that's guaranteed by the conclusion. And so we're given here that we're supposed to be using Rolle's theorem. We need to verify that the hypotheses for Rolle's theorem are met first. So we'll look at the hypotheses. And the hypotheses, there were three of them for Rolle's theorem. The first two were the ones that were shared by the mean value theorem. We need to assess continuity and differentiability. Well, this function here is a polynomial, and polynomials are continuous and differentiable everywhere, so we're looking at those first two being met. So f is continuous on the closed interval 1, 3, and we also have then that second one, f is differentiable on, not closed interval anymore, though it would be the open interval 1, 3. And so then the third one that we have to verify is what's happening at the endpoints. Are those endpoints roots? And so we've got to individually plug in 1, and we've got to plug in 3 because those are our two values or endpoint values for our interval. And so when we plug in 1, we've got 1 cubed minus 4 times 1 squared plus 3 times 1. So we're looking at 1 cubed is 1. Minus 4 times 1 squared would be minus 4 times 1, so minus 4. And then plus 3 times 1 would be plus 3. So we've got 1 minus 4 would be negative 3, plus the 3 gets us to the 0. So far so good. We've just got one more thing to check. So when we plug in the 3, we've got 3 cubed minus 4 times 3 squared plus 3 times 3. So 3 cubed would be 27. And then we have minus 4 times 3 squared, so that would be minus 4 times 9, so minus 36. And then we have plus 3 times 3, so plus, 3 times 3 is 9. Okay, so we're looking at 27 minus 36 plus 9. That does in fact give us 0. And so yes, hypotheses are met. Okay. So we see there that Rolle's theorem involved just a little bit more for hypotheses because we had to plug in the endpoints, but for this case we have hypotheses are met. So as soon as we have that the hypotheses are met, we want to start looking at our conclusion. So our conclusion here is we're looking for a particular c. And that c has to be between 1 and 3. We've got to keep that in mind. But we've also got to algebraically be able to solve for it. And here we have that we needed f prime of c equal to 0. Well, if we're going to be looking for c's that satisfy this, we're going to need the derivative function to work with. So we have the function there, the polynomial function f of x, so let's take its derivative. And for polynomials, it's just power rule with constant multiple and addition subtraction, fairly easy to take the derivative of. So we have 3x squared minus the 4 times 2 for the power is 8x, and then plus 3. That would be our derivative. So really what we're doing here is we set the derivative equal to 0 and find the x's that work. So when we're looking at that derivative equal to 0, we're looking at a quadratic equal to 0. So to solve quadratic equations, we either have to factor the quadratic and set each factor equal to 0 using the zero product property, or we can always use the quadratic formula. And for this one, we could think about whether or not it would factor, but I don't see it right off, and it turns out that it doesn't factor nicely. So let's go ahead and use the quadratic formula. So for the quadratic formula, we would have x is equal to negative b, so negative the negative 8, plus or minus the square root, and we have b squared under it, so negative 8 squared. Notice how I'll put the negative 8 completely in parentheses because I want to square the negative 8, giving me the positive 8 squared part there. So I have, let's see, negative b plus or minus square root of b squared minus 4 times a is 3, times c, which is also 3. So let's extend our lines here. And that's all over to a, and a again is 3. So we've got a little bit of work to do here to clean this up, but we've got the -8, which would be just the +8 on the top there. Plus or minus gives us our two solutions here to the quadratic, and when we're working on cleaning this up, we've got the 8 squared, which would be 64. And then we have -4 times 3 times 3. So I see that as 4 times 9 for the 3 times 3. So 4 times 9 is the 36. And then it's all over the 2 times 3, so that's all over 6. So let's keep going. We've got underneath the square root that we can handle. So we've got 8 plus or minus. The square root now is 64 minus 36 would be 28 under the square root. And then it's all over 6. So as we're still trying to clean this up a little bit here, we can see whether or not the part underneath the square root has a perfect square factor, and it does. 28 is 4 times 7, with 4 being the perfect square. So if we're looking there at 4 times 7 under the square root, when we simplify that, it would be, we would take the square root of 4 to bring out the 2, leaving us with the 7 under the square root, and all of that is over 6. And then we see on the top, it's separated with the plus or minus there, so we really have to think about factoring this thing on the top if we're going to reduce the fraction. So we see the common factor of 2 that would be in the 8 and the 2 root 7. So it would be, if we pull out a 2, we'd have left over the 4 plus or minus root 7 all over the 6. And so then the common factor of 2 cancels on the top and the bottom, leaving us with 4 plus or minus root 7 all over 3 now. Now keep in mind that's 2 answers, and it's certainly possible that we have 2 answers because our C doesn't have to be unique for these problems. But once we algebraically solve for the answer, we need to check to see if each one of the ones that we algebraically solve for, if they all land in the interval. And it's the interval given there, the 1 to 3. And so what ends up happening, we've got x equals the positive case, the 4 plus root 7 over 3. If you put that in your calculator, that value is approximately 2.215, which is in the 1, 3. That 2.215 is between 1 and 3, so that is a viable option. But in comparison here, if we take the minus case, we've got 4 minus root 7 over 3. That value is 0.451 approximately, and that is not in. So I'm going to do a little dash through my is an element of 1, 3. So really our only C value here is this value right here. I'll go ahead and box that value.